Hello, I am Václav Novotný and welcome to the tutorials of energy sources and conversions. This video will be focused on Carnot cycle and ideal gas. Okay, so now we are getting to the parts with thermodynamic cycles. That means systems which convert between each other heat and work by either as a so-called right-turn cycle, converting heat or transferring heat from high temperature level to low temperature level while creating work output, or left turning cycles having work input while transferring heat from lower temperature level to high temperature level. The first thermodynamic cycle which we will look at is the Carnot cycle, because it's the specific cycle or specific systems that stands out because of providing the theoretical limits of the efficiency between two temperature levels. The Carnot cycle is shown here on these two diagrams: PV, pressure volume, and TS, temperature entropy. Now let's go through the specific thermodynamic processes in the cycle. From 1 to 2, we can see at the TS diagram that the process has constant temperature, and we can see that the pressure is increasing. So it's isothermal compression. For this isothermal compression, we need to have work input, and to ensure that the process is isothermal, so also there needs to be heat output. Then from 2 to 3, we can see that it's isentropic compression. Pressure is increasing while the entropy stays constant, and isentropic process is also adiabatic. That means there is no heat exchange with the surroundings, with the outside of the system. But to make the compression, we need to input some work. Then from 3 to 4, we can again see that it's an isotherm, but now we have the heat input and the pressure is decreasing. We are creating some work, so it's isothermal expansion. And then 4 to 1 is isentropic expansion, again no heat exchanged with the surroundings, but only work produced. Now let's have a look at calculation of the efficiency. Always efficiency of the cycle is the net work divided by the heat input. From the energy balance, which we have seen for example in the last tutorial, the work output needs to be the difference between heat input and heat output. Here QP and QO, and it's still divided by the heat input. Now, looking at the diagram, we have the heat input between points 3 and 4 and heat output between points 2 and 1. So the heat input is temperature 3 times difference in entropies S4 and S3, and the heat output is temperature 1 times difference of entropies S2 and S1. You can also note that as in the TS diagram, it's a rectangle, so the difference between entropies 3 and 4 and 2 and 1 are the same. So this whole system simplifies to T3 minus T1 over T3, or just 1 minus T1 over T3. You may wonder why the heat is the temperature times difference in entropy, and it's derived from the second law of thermodynamics, where in the ideal case, in case of reversible changes, which are all the changes in ideal Carnot cycle, dq equals TdS. And since the temperature is constant, so we can also write that delta Q is temperature times delta entropy, or we can write it also in lowercase in unit parameters. So works for both absolute heat and absolute entropy, and unit heat and unit entropy. Now let's go to a problem which we will calculate. We will have 1 kilogram of ideal air which performs a Carnot cycle with following parameters. We have given the highest temperature of 900 kelvins, lowest of 300 kelvins, and we have also the pressure levels, the maximum pressure being 58.8 times 10 to the 5 pascals, and lowest pressure 0.98 times 10 to the 5 pascals. This meaning roughly 1 atmosphere. And what do we want to determine? We want to get the work of the cycle, efficiency, pressure and volume in typical nodes of the cycle, heat input, rejected heat, and for calculation we will assume ideal gas, specifically it being air, which will have specific gas constant 287 joules per kilogram and Kelvin, adiabatic exponent 1.4, the so-called kappa, and specific heat capacity 1005 joules per kilogram and Kelvin. Now what will we need to perform the calculations? We will need ideal gas equation, PV equals RNT. Then the isentropic change of ideal gas, PV to kappa, is constant. And if we combine these two equations together, and so we can get, after some manipulation, this expression P2 over P3, or P2 equals P3 times T3 to T2 to kappa over 1 minus kappa. So these are some of the equations that we will use. And then we will use first law of thermodynamics in the form of enthalpy, dH equals dQ plus VdP. And since we will use this for the isotherm, where dH, which can be rewritten also as Cp delta T for the ideal gas, equals 0, so we can see that the dQ, change of heat, is minus VdP. So for the heat transfer of this isotherm, we can then write for example, the heat input as integral from point 3 to point 4 from dQ, which means integral from 3 to point 4 from minus VdP. Now we can do one modification here from the VdP, because since the R is constant, T is constant, so from the ideal gas equation, PV would be also constant. So we expand this term by 1, multiplied by 1 in form of P over P. So we will get actually PV divided by P multiplied by the dP. And since this PV is constant, it can go in front. PV equals RT, so we get minus RT times integral from 3 to 4 dP over P, which is logarithm of P. So getting there the limits, the boundaries, we get minus RT logarithm P4 over P3, or if we get rid of the minus sign, so RT logarithm P3 over P4. The same method can be actually used for the heat rejection, also isotherm between the points 1 and 2, getting here the form of RT logarithm P1 over P2. So now let's calculate all the parameters for the nodes and for all the results that were required in the problem statement. So here let's draw a table with the columns for temperature, pressure and volume. and let's immediately put in what was given, or what we know. We know that the temperature limits, the low temperature in the cycle was 300 kelvins, that's temperature 1 and 2, so it's 300. Let's also highlight that we already know that from the problem statement, we don't need to calculate it. And the temperature 3 and 4 was 900 kelvins. So temperature 2 is same as temperature 1 and temperature 4 is same as temperature 3. So we know already all the temperatures. Now what else was given? We had the lowest pressure in the system, and that is, as we can see in the point 1, where this pressure was 98 kilopascals. And also we had the pressure in the highest point in the cycle, which we can see here is at the point 3, which was 5.88 megapascals. So 5.88 megapascals. Now what can we do with this? So first we can go to the volume at the point 1, which we can get from the ideal gas equation, where the volume equals RT, like this, over P. So the volume will be 287 times temperature divided by pressure. So the same thing can be done also for the point 3. And now we are missing the points 2 and 4. Meaning, and how to get to the pressure at that point. For example, it's from the, let's say, pressure at 2 is from the combination of ideal gas and the equation of the adiabatic, reverse adiabatic change. So we can get it by going adiabatically from or isentropically from the point 3 to 2. So its P2 is P3 multiplied by P3 over P2, and this will be to the power of kappa divided by 1 minus kappa. So that's pressure at the point 2, and very similar we can obtain the pressure at the point 4 from the pressure at the point 1. So basically we just can change the respective values here. P4 is P1 T1 over T4. So let's put it in our calculation. So pressure at the point 2 is pressure at point 3 multiplied by temperature 3 divided by temperature 2 to kappa 1.4 divided by 1 minus kappa. And similarly here, pressure at the point 4 is pressure at point 1 multiplied by P1 over P4 to the power of kappa 1.4 divided by 1 minus kappa. And now we have temperature, we have pressure, so we can again apply the same equation for getting the unit volume. It's the same as in the case of point 1 and 3, and by that we get the parameters in all points of the cycle. Now let's get to the heat input, Q in. We had derived that the heat input is RT logarithm P3 over P4. So let's put it, for example, here, Q in equals R 287 times T heat input is at temperature 3 or 4, which are the same, times logarithm P3 over P4. So we get the heat input for the 1 kilogram of the air would be 64 kilojoules. Now the heat output will work similarly, where the Q out was RT logarithm P1 over P2 . So again, R times temperature of the heat output times logarithm P1 over P2. And from this we get that this is positive, so it's the heat input into the cycle. This is negative, so it's heat output of the cycle. Now, what is the net work output? Given the energy balance, nothing can, it is a steady state, or it is a cycle that performs just once. So energy cannot get lost or appear. There is no other heat or work input or output. So it will be the sum of these two, or difference of this and this in absolute value. Now let's have a look at the efficiency. Efficiency of the cycle is always ratio of the work output. We can have it in unit parameters. So some net work output divided by heat input. And we have said also that the efficiency of the cycle should be 1 minus T1 over T3. And also the net work output, same as we expressed it here, is the heat input minus heat output divided by the heat input. Those are different expressions for the same thing. Just when you do some calculation of real systems, so be careful about applying this heat input minus heat output, because then you need to really express the heat input and heat out, and especially the heat output of the system properly, and you might still neglect some other efficiencies of the work before the you have the actual network of the system. So now let's calculate this efficiency over here. So network output over heat input, and get reasonable amount of decimals, and we get 66.6 periodic of percent, or 0.66. Now let's check if the other expressions will also apply. So let's try 1 minus T1 divided by T3. We get the same, and also heat input minus, and now careful, this heat input minus heat output means absolute values. So absolute of heat output, and divided it by the heat input, and you still get the same result. So by this we have finished the Carnot cycle, the ideal cycle obtaining theoretically the highest possible efficiency of converting heat to work. And in the next tutorials we will have a look at different cycles which are really implemented in the real life. One of the reasons this cycle cannot be implemented is first, all the processes are, all the real processes are irreversible. So, for example, 2 to 3 will not be exactly isentropic, but will be a little bit departed from that. But most importantly, the isothermal heat addition and isothermal heat rejection, with here being expansion, here being compression, is practically not achievable unless you will have some really super huge piston systems working in very slow speed, and then it's technically unfeasible. So that's it. See you next time.